this week we're talking about reflection. I just want to ask you a question, which is like the classic physics question first, which is how is it that a mirror understands to flip you from left to right, but not top to bottom? Right. So, for instance, I have a mirror right here. Oh no, is it gonna the? Okay, actually, it's okay. If you see here, my reflection is waving his left hand, right? And I'm waving my left hand. Okay? Why is it that my reflection knows to wave his left hand, but he's flipped left to right, but he's not flipped top to bottom, right? If I rotate the mirror, it doesn't make a difference, right? I'm it's still a left to right thing. The mirror doesn't rotate, doesn't flip my head and my toes. It only ever flips this direction, right? And this is a common physics question you get in interviews, like when you apply to university to study physics. I know, I'll just give you the answer. Here's a book, right? It's a good book, Dynamics and Relativity. Now, what's going to happen is, I'm going to turn around the book to show it in the mirror, and you'll see that the text flips, right? You see it says Dynamics and Relativity the wrong way around. It says Skimanid Dna. You see, it's flipped left to right. However, it's flipped left to right because I flipped it left to right, right? If I flip it down to up, right, then now you see it says Dynamics and Relativity. You see the word dynamics, you see the word relativity, right? But you see it's the right way around, right? It's just upside down. So what happens normally? Well, why do we see each other flip like that? Why do we flip left to right? Well, let's look at this. This is something I made earlier. Ooh, hello, wowee, ABCDFG. Right? We're gonna, again, if we turn this, right, left to right, like this, you can see that, if I can, it's difficult to, wait. So I flip this left to right, you see that the wowee is flipped left to right, if I can get it to actually appear. Can I get it to appear? You can kind of see that, right? And same for top to bottom. But what a mirror does, it doesn't invert us left to right, it inverts us front to back. So for instance, right now, on the front we have this hello wowee, and on the back we have white, right? But if we look in the mirror, then all we see is white. We don't see the front part of it. So now let's invert this, right? And it's still the same way, you know, it's the way around you'd expect to read it, right? So now this is in front, and then, wowee, you know, it's the right way around, because it's only flipped front to back. And the fact is, if you flip a human front to back, it's the same as rotating our scale in Unity by transforming the Z scale through itself. And then if you flip yourself front to back, your right hand will become your left hand, and vice versa, because we're symmetrical beings-ish. So that's what's going on there with mirrors, right? So, and now let's start the actual proper lecture, because people get asked that a lot, and it's I don't think it's necessarily an immediately intuitive answer. Obviously, that'd be an easier demonstration in real life if you were standing next to me with a mirror. Actually, I suppose in a real life lecture, in a hall, it would have been impossible to do that demonstration, right? Because the mirror would be facing, it wouldn't be facing all of you, whereas I could control what the camera sees. But yeah, I mean, you can. I only had to put the white card there because of the like. You can't even see the wowee if I do it like that. But if you just write wowee yourself and hold it up in the mirror, you'll just see. You can't see this, but you'll just see the exact right. You'll see the same thing. It'll look the right way around. Anyway, wowees aside. So reflection. That's what we're doing today. And by the way, reflection not only works for light, right? Reflection works for momentum. So if you have a perfectly elastic collision, Alex, can you spell? Elastic collision, then it's the exact same as having, momentum. Having like a photon collide. Right. So, but let's examine the photon, right? Because this is the generic example. So we have. Okay, actually, I'm not gonna do that. For now, I'm just gonna draw a line. Right. Yeah, that's fine. Actually, okay. I've got to be careful with my straight lines for this lesson. Because you know what I'm like, not caring about straight lines, but today they matter. Okay, so when a photon approaches, like a mirror, for instance, something that's actually going to reflect it, right? It bounces with this angle of incidence, okay, and it reflects with this angle of reflection. Then we can call this alpha, and well, you can see as well, if we were to continue this line onwards, how many down was it? It was 1, 2, 3, 4 down, 3 up. Wait, no, 3 across, 4 down. Okay. Yeah, sorry, I'm gonna be counting my numbers constantly. Right. Okay, first of all, the law of reflection, which is a physical law of the universe, a new law for you, because all of the other laws are pretty much derived from, conservation of energy and momentum, which is all derived from conservation of energy. But if the law of reflection is a brand new law for you, and it states that the angle of incidence equals angle of reflection. So this angle is always equal to this angle, and because of how, things work, this angle is always this angle too. And so this angle is equal to this angle, and these are all alpha, where alpha equals pi over 2 minus theta, right? Because this is pi over 2, of course, is 90 degrees, but we're not using these anymore. We're talking pi's now, right? Pi is a quarter turn. Okay, so you'll notice that this, right, this vector here, that the attacking vector, let's call it, and the returning vector have the same x component, right? The x is going, it's going at the same speed, but the y up to this point becomes minus y, right? So originally it was here, now it becomes here. Okay. Just gonna quickly make it clearer. We'll go 2 and 4. Well, 2 and 8. Okay, I'll just put it there. You see this time, right? Clearly, alpha, 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 right? Theta, theta. Right. Just to make that abundantly obvious. Right, I just wanted to, because obviously these ones, the angles are quite similar anyway, this theta and this alpha, so I just wanted, to me, when I'm thinking in angles, it helps me to draw a really exaggerated diagram where the angles are really small, so I can see, like what it would look like in the more extreme cases. But it's probably obvious. Right, so let's get into things. We have, okay, this time we're just going to go at like 45 degrees, because whatever, you get the point. Okay. We have some D, which is the direction of the original, you know, the photon or whatever we have, the particle, right? And then we have some R, which is the reflection. Okay? Now, you can see here, this, right, is going to be the normal of the vector. Okay? So let's, I mean, you know, it doesn't have to be this way around. It could have looked like this, you know, and then the normal would have gone down the middle here. Okay. So this angle of incidence is the angle made with the normal, right? Except it's in the opposite direction, right? Because if you see here, this is theta here, right? We can see that this is D, and as you know, when you take the angle closest to it, the adjacent angle is cos. So if we want the components of this split into x and y, we can say that this thing is d cos theta here, right? And I believe that's alpha, right? So we've got yeah, that's right, isn't it? Right. Maybe it's somewhere around. I'm pretty sure that's right, but right. So d cos theta is going up here, and down here we've got minus d cos theta, right? And we can say that, okay, imagine you dot, right? We won't always be able to grab this angle, right? It's not, we're working in a game engine, it's not convenient to work in angles, it's convenient to work in vectors. So what we're going to do is, we're going to say that x, right, if this is theta here, then x is d cos theta. Oh, sorry, yeah, that's sine. Right, y is d sine theta. Right, where is that the same thing? No, that's definitely alpha. Right, that's alpha. Yeah, okay. So I've written the notes down wrong. I knew it was right. Okay. You can see that when we swap it round, it's going to be x is sorry, I've done it. Why am I doing this wrong? Okay, either way, x is going to be the same, right? And y is going to be the inverted. It doesn't really matter which way around it is, because we're not even we're not even going to use trig functions. We're going to use dot products. Is the point I'm making, right? So if you take the d, right, this vector, and you dot it with the n, right, you will see that you will get the d in the upwards direction. Okay, right, and this is a normalized vector, so we don't need to. We could have dotted it with the n magnitude, right? But if we dot that, we find the component we find the upwards component of d, right? Then what is important to note is that we have some ijk system of coordinates, right? So I is rightwards, j is upwards, right? So I is the same as 1, 0, and j is the same as 0, 1. Okay? It's just a vector that tells you what direction something's in. So in this case, you'll see that the normal, right, is opposite to the j vector. So the j vector is going directly up, and the n vector is going directly down. So in this case, we can say that n equals minus the direction of j, right? If j is there, then n is here, right? So if you take this dn, right? Okay, this is drawn badly. If you take d dot n, you get the upwards component. Well, I mean, you get the downwards component of d, right? Because if you were to dot d with y, right? If you did y dot, this j component, you would end up getting sorry. If you I'm going to use a different color because I made a mess, right? If you take d and you dot it with the j component of this, like, of the world, you will find out what percent of d is going upwards, right? Now, well, not what percent, but like the magnitude of it in the y direction. If it's made up of some x and y, you'll find out how much of it is y if you dot it with the y. However, we've dotted it with n, which is the downwards vector, right? So we actually found the minus y component, right? But now if we multiply it by n again, right? So this is going to produce a scalar, right? This is not a vector because it's a dot product. It produces the magnitude of this vector, right? So we've got the magnitude of this, which is going to be negative because it's going up. So if we dot it with n, which is down, we're going to get a negative value. We're essentially going to get the same thing as if we dotted it with the up vector, but we'll just get the negative value. And then we're going to multiply it by n, right? Which is negative itself, right? So we're getting a double negative. So we've got, we've got this n that we're multiplying by, which is minus the j. So we've essentially got, if this thing upwards, okay, I need a new slide, right? If this thing upwards is d cos theta, right? Then when we do, and this is d sine theta, okay, and this is our vector d, right? Then when we do the dot with the n, right, d dot n, we get minus d cos theta, right, because it's in the opposite direction. However, then when we do d dot n and we multiply it by n again, we now get d cos theta in the j direction, because j is minus n, because they're opposite each other. Thus, j is upwards, n is down. Okay, I hope that I explained that properly, even though I got rattled because my stupid notes are wrong. Right? So, you can see that this thing, this d dot n multiplied by the n vector, gives us the y component, aka if we were to rotate this, right, it would give us this component. So it doesn't matter. In this case, it's equal to y because we're looking at a vertical slice. But if we were turning it on its side and looking at it this way, we would notice that we have the same thing. We have, like, if we were to convert it and anti-quaternion it back to its original position, right? If we were to transform this to a horizontal from this, if we were to rotate it that way around so it looks like this, we'd still get the right thing because we're using dot products now. So this thing is giving us our local y value. And we're going to keep working in these local values because it's easier. So d is made up of x times I plus y times j plus z times k, right? So these are just values, right? Or we can even call it dx, dy, and dz, right? And these are vectors. Right, that's d dot x. You know, it's not the it's not like a integral. That's d dot x, the x component of d, the y component of d, and the z component of d, multiplied by these unit vectors. So again, that's the unit vector I. So the unit vector I is equal to 1, 0, 0. Okay? J is equal to 0, 1, 0. K is equal to 0, 0, 1. So when you look at this equation here, right, and we've got, in fact, let's just, to not confuse you, not call them D again, let's just call them X, Y, and Z, right? X, Y, Z. We've got xi plus yj plus zk. Well, let's do x multiplied by I, we get x, 0, 0. So that's xi. Yj is equal to y times 0, 1, 0, so 0, y, 0. And zk is equal to 0, 0, k. I mean z, right? So you can see that these things are scalar, these things are vector. These things are magnitudes, these things are directions. Right, so if you add all of these together, you see that, you know, x plus 0 plus 0 plus y plus 0 plus 0 plus 0 plus 0 plus z, you end up with that. Right, so D is this. Okay? And it's useful to think of things like this. So we're gonna, for instance, right, say you have D is made up of xi and yj, right? So in this case, we're not doing 3D. Right? So we can see that in our example, D is xi plus d dot n times n. Right, remember we replaced this for the y component. So we determined that yj in our example is equal to this. Okay? Now, if we want to find what x is, we can just subtract it, right? xi equals d minus d dot n. And so what that means is, if you imagine we have some triangle and we go up by d, right? And then we subtract this, which is essentially y, boop, then you see we're left with x, right? If we started adding d and then subtracting y, we just end up with x, right? Multiplied by the I direction, which is rightwards. Okay, I hope that's clear. Right, and again, n is minus the y direction, right? So the n is down. So this is kind of positive in that direction, right? So what we can say here is, okay. We've calculated this, right? X is equal to that. If that's true, okay, if xi is equal to d minus d dot n times n, then that means that d is equal to, this is the x component, d minus d dot n, right, plus the y component, which is d dot n. Okay? So now you see, before we were working in x's and y's, but now we have no x's and no y's. Right? The whole thing is just irrespective of the direction. Like if we, you know, whereas before we could call it, this x component is going to be d minus d dot n, right? And this y component is going to be d dot n. Right? In this example, this vector down here, well, okay, the easiest one is this one. This normal vector is d dot n, and this vector is d minus d dot n. over here. Okay? So every single vector is made up of this chunk and this chunk. I really hope that I explained this bit well enough that you understood what I was talking about. I could do one more time if it's not clear, but I hope it is. So, okay, let's look again at a reflection. Okay, so we have some angle that's going through here, right? And it gets reflected. Okay, you'll notice that what the reflection does, again, if the x, right, if the d, this d vector, in this case, is equal to xi plus yj, right? Now, the reflection vector, this, is equal to xi, again, it's got the same x component, but it's just flipped in y, minus yj. You'll notice that, like, if we draw it, again, if we draw here, this is if we don't subtract, this is just x plus y, right? This vector is x plus y minus y, and this vector is x plus y minus 2y. Right, if we you see the difference between these two, right? I mean, if we put them equal to each other, we've got d minus yj equals xi, right, from here. And then we can get the xi here. R plus yj equals xi. So therefore, r plus yj equals d minus yj. So r equals d minus 2yj. Okay? So r is the same thing as the original vector d minus its own y component twice. Right? It goes up, and then originally it was going to go this way, but if we subtract y once, it would go back to neutral, and if we subtract y again, it will return back from whence it came. Okay? So we now know this relation. This is the vector we want, but we don't want it in terms of y, because that only works in this frame where we're, you know, this way around. We want something that's going to work in every single direction. Right. So we're going to say that r equals the x the x component. So remember, the x component was d minus d dot n times n, which is essentially the same as saying the full vector minus its y component, right? And then plus the y component, d dot n times n. Right, so this thing's y, this thing's x, right? Minus two lots of y, right? So minus 2 d dot n times n. Okay? So you see that this r thing is equal to this d, and then we've got minus d dot n dot n plus d dot n dot n minus 2 d dot n dot n, right? So this cancels, and all you're left with is this. So we got 2 times that. Okay? And then that's it. That's your reflection vector. So you just take your original vector, and one thing you can do to make this even easier is to say, hey, if we do d minus 2d dot n, right, this is computationally quicker to then just call that n squared, the magnitude of it squared, times n. Right, so we don't need to take we don't need to get the normalized thing anymore. Because remember, like, when your computer calculates this vector, we'll call it c, and this is a and b, then it will calculate that c squared is a squared plus b squared. So therefore, it will then do c as the root of a squared plus b squared, right? However, it's quicker, you know, to just leave it squared, because then you're just squaring two values and adding them together. If you do a square root, that's an additional operation. So you see this, even though it has a squared in it, the computer's only doing one thing. It's just adding two numbers together, and then you're multiplying. So you do the d dot with n, then you multiply it by n, and then you do this. Luckily, Unity, when we have collisions, when stuff bumps into each other, it's already normalized. So the magnitude of this is already 1. Right, so we just get 2 minus d dot n, okay, times by n. And the whole thing is divided by 1. Right, so let me write that clearer. D minus 2 d dot n, n. Right, that will give you the reflection of anything. So if you bump into a wall in Unity, you know, you have your bow and arrow or something, or you have a light ray, you're using a line renderer to draw lines on a mirror, right? It would help to cache your velocity, right, before. So, because it's going to lose all its velocity as soon as it collides. But let's say your bounciness, right, is 0, and you cache your velocity beforehand. So at the end of fixed update, right, at the very bottom of it, you say that your cache velocity is your r dot velocity. Then you will know the velocity with which you hit this object before, right? So you go bang, and you want to reflect it back. Well, you can say, okay, my previous velocity, cache velocity, right? My new velocity is equal to my cache velocity, so d, minus the vector 2 or vector 3, depending on if you're working 3D or 2D, doesn't really matter, dot between your cached velocity and the normal of the thing you hit. So, you know, col.normal, right? Obviously, you need to get, like, the hits, the point of the hits, you know, like hit dot context dot of 0 dot normal, right? You dot these together and then multiply it by col.normal, then your velocity will reflect. Okay, this formula will reflect things for you. Right. Yeah, go on. Yeah, right. So what we can do is, that works if it's elastic, but if we want to just, you know, take off, if we want an inelastic collision, the angle's going to still be the same, right? If we bounce off this wall, right, the reflection vector is still going to be the same. The only thing that's different is going to be the magnitude of that vector, right? So if you want this to lose half of its energy, then you can just do r dot velocity equals half of this, you know, and that will give you the same thing as a coefficient of restitution of 0.707. You lose half your energy in one go. Oh, sorry, no. Yeah. 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 Wait, so what things are give me are you talking about colliding with a wall, or are you talking about two things colliding with each other? Okay, so which way do you want me to draw my wall? Horizontally, vertically? Okay, right. And now where do I put the ball? Right. I see what you mean. So you're saying that in the x-axis, momentum is conserved and is not going to change, but it's only in the y-axis. Okay, yeah, you're right. So remember that this thing is equal to, okay. Right, well, we can just use this formula that we have here, right? So we got, this is the x, this is the y, and this is the minus 2 dot x. So you've essentially got your initial d here, right, is the x and it's y, and now you this time will only reflect off the y. So instead of subtracting 2 times the y, this thing we'd subtract however much. We do 2 times like the percentage. So for instance, if you wanted it to lose half of its momentum, then you'd multiply this by half, right? And then that would give you, or would it? That's a very good question. Yeah, so the angle would change, right? So because it would end up here, right? It'd end up if it lost half its momentum, the angle would end up here, right? So it's you're going to take your what would happen is, right? Okay, here's what would happen. That's a very good question, right? So your x, right, your xi in this case is equal to d minus d dot n times n, right? And and that would say the same, right? You'd have the same thing here, right? But your y, j, would be equal to originally your your initially it would be equal to this, right? But at the end, it's going to be equal to 0 minus d dot n multiplied by the bounciness, essentially. So like, say you have like, you want it to lose half its energy in this direction, like half its velocity. Okay, so you want half bounciness, then it's going to be 0.5 on this component, on top of the original vectors, right? So your r is going to be, d here is this xi plus this yj, right? But then you're adding r equals this xi, the original xy, plus the yj, minus, well, not plus the yj at all. We're not going to add this yj because it's 0 here. We're just going to subtract the bounciness times this, right? So for instance, we're going to have xi, so here d minus d dot n times n, right? And then so that gives us x, and now y is 0, and now we need to subtract half a y or whatever. So let's say we'd call it e, bounciness, right? Times d dot n. Okay, and now that will give you, a collision in which you only lose half of your momentum in just this direction, right? But if you just wanted the entire thing to sap your energy completely, like, most of the time I just wouldn't do, like, I personally wouldn't send it off at an angle like that. Like, if, like, I wouldn't put it in a situation where it only robs your x velocity and doesn't rob your y velocity, because I'd just make it, bounce off and be like, okay, well, now it's a weaker bounce. I'd just give it the same direction. Personally, from a game design perspective, I would try and keep the law of reflection going, because if someone fires their arrow at this wall, they're rarely expecting it to like ping off in this direction, right? They're expecting it to come back where it came from, even if it's coming off at a weaker magnitude. But if you were to, you really do want to put it off at just a smaller x magnitude and not a smaller y magnitude. It depends what happens in the collision, right? Because with a wall, it is inelastic, as you say, and momentum's not conserved anyway because the y momentum's flipped. So it really depends how much energy the wall even imparts on it. So it's not like there's some physical rule that, oh, this is how much energy the wall will give to it. It's like, it just depends, right? But if you're playing snooker or something, you know, when you're playing billiards, it bounces off at the same angle it came from, right? Even though the cushion, the ball will lose a bit of its original momentum, right? When it bounces off, but it will still. You don't expect it to suddenly just go flying off to the side, right? You expect it to come back where it came from. Apart from the fact that the ball itself might be rotating, and that when we've not covered rotation yet, but if the ball itself is rotating, then it's gonna impart additional momentum, and so it's gonna move slightly differently. But if you move it in a straight line, right, it's just gonna get a bit weaker. It's just gonna lose its energy, and we can just take. In my opinion, it's better to do it in that way. Well, what I wanted to do was show an example, but it's going to take forever to get through. So, I'm not even sure we need to do these. You know, maybe I'll set it up for the next lecture, and then we'll see if we can just like storm through it very quickly next time. So what I'm going to do is I'm going to draw the mirror that we're going to have. So the mirror's going to look like this, right? Our vector, oh my god, our reflection axis is, no, that's the eraser. Our axis of reflection is through here, okay, and the horizontal to this is there. No, that's bad. Right, and the vertical to this is there. And we're going to have some ray coming in. Right, from this angle. So, this way. Okay, and it's going to get reflected this way. 4 and 2, right? Right, and we can in fact just clean up this whole side because we don't care about this. Okay, so this is your mirror. This red line is your normal. Okay. And that goes off to it. It's almost like infinity times the normal, right? Because obviously the normalized vector would go to here. Okay. And then this is our d vector. This is our r vector. And we can see that the normal, right, is equal to minus 0.707 minus 0.707, right? And if this is d, right, and d has some value theta here, right, then, and this theta is going to be equal to pi over 8, right? Because if you look at it, this vector would be pi over 2, right? That's a quarter pi, 90 degrees. Then this vector would be pi over 4, and this vector here, where we're going 2 across 4 up, that's pi over 8. Okay? So this d is equal to, right, cos pi over 8 sine pi over 8. This this n, right, is equal to minus 0.707 minus 0.707. Of course, the reason being is because that's minus root 2 over 2 minus root 2 over 2. Obviously, the vector itself, you could say, is in the direction, minus 1, minus 1. But to normalize it, we do this, because if you square this thing, you get minus 2 over 2 squared. Oh, well, you get 2 over 2 squared plus 2 over 2 squared, which is 2 over 4 plus 2 over 4, which is, 0.5 plus 0.5 is 1. Right, so that's just the minus 1 vector normalized. So this is our n, and this is our d, right? Then our final solution, r, is going to be d minus d dot n multiplied by n divided by 1, but 1 is 1. So this thing is the same as okay. We're really quickly. I just want to quickly put in the values so we set us up for next lecture, right? If you do sine of cos of pi over 8, because remember that was our x, you get 0.924, and if you do sine of pi over 8, you get 0.383, right? So this thing, this d is equal to 0.924, 0.383, right? Minus 0.924, 0.383 dot minus 0.707 minus 0.707 times by 0.707. Sorry, no, that, right? Okay, that's divided by 1, and this produces a scalar, right? So that will give us our r vector, and we'll calculate it next time really quick. But I've already run over, so we'll just tag that on the end next week. But I've given you the formula anyway, right? We've already come to the conclusion. So if you wanted to do your own balancedness formula, right, you've already got this. And you could explore what we talked about. Like, you could purposely say, okay, I want to take away its x. I want to take its parallel momentum to the wall, but I don't want to take away its vertical momentum. But normally when you do that, it's because the thing's spinning. Like, in general, you would expect it to come off, to reflect at the same angle it hit the wall at, unless it's rotating. Right. But we can go into this more if you want. There is another topic we didn't cover really, which is momentum in 2D, which I suppose we should do really. But I just wanted to take you on a detour because we've done like 8 lessons of momentum in a row, and I'm sure you're all bored of me writing M1, M2 equals M1, M2, right?